Okay, welcome to round 2 of Unit 8, Virtual Unit 8. I'm your host, Mr. Kuiper, and today will be a lot shorter than last time, I assure you, especially if I stop making jokes, because like paper, my jokes are terrible. So, I actually did start this already, and I got 10 minutes in, and the connection timed out. So, some of this will already be written for you just because I'm not going to rewrite everything all again. But here we go. Last time, if you remember what we talked about what it meant for two figures to be similar. We said that two figures are similar if their corresponding angles are all the same and if corresponding side lengths are proportional. So that's going to be key here as we go forward, just to remember that definition of similarity will always hold. Okay? And we're going to go a little bit to first semester here and kind of go back to the thing that you all love with proofs. And we won't be writing formal proofs, but the ideas behind proofs of giving a statement and providing reasoning will hold true here. Okay? So what we're going to be doing is we're going to be looking at different ways to prove triangles similar. And in 8.2 specifically, we're going to be proving triangles congruent by angle-angle. Okay, so that's what the AA stands for, is angle-angle. So the box right here highlights what, what angle-angle similarity theorem is. And basically what it's saying is if you can prove that in any two triangles you have two pairs of corresponding angles that are congruent, then you can conclude that it's similar. Okay, and there's a formal proof of this on page 428. I think if you take a look at that, it would be helpful. Just really informally, if angle A and angle D are congruent, B and E are congruent. We don't know anything about C and F yet, but we know that C and F have to be the same. Why would C and F have to be the same? Well, if I label this with an X, this I can label with an X because they're the same. Same thing here with the Y. Both of these triangles have to add up to 180. So if I take 180 and I subtract X and I subtract Y, I'm left over with the same thing. I'm left over with angle C and I'm left over with angle F. So angle C and angle F would also have to be the same. Therefore, all the angles are the same. Therefore, it's similar. Okay? So you actually only need two to prove similarity, and that's what we're going to look at in these examples here. Okay. So in example 1, it says, determine whether the triangles are similar. If they are, write a similarity statement. Explain your reasoning. All right. Well, if you take a look at these figures, or the figure underneath, we're trying to find angles that are congruent. Well, I think it's pretty clear to say right away that one of our angles here, angle D and angle G, those have to be congruent because they're both right angles. So since it's labeled on there already for you, don't have to do much work in getting the fact that angle D is congruent to angle G because they're both right angles. Okay. So that's already one pair of angles that we have. If we can just show one more pair of angles congruent, then we're done. We don't have anything labeled as congruent, so what I'm going to first try to figure out is, well, if I know this is 26 and I know this is 90, I can actually figure out angle E. How can I figure out angle E? Well, the measure of angle E, since there's 180 degrees in a triangle, I can just take that 180, subtract 90, subtract this 26, and what I'm left with is 64 degrees. So I've just shown that angle E is equal to 64 degrees. Okay, and the reason that helps me is because if this is 64 degrees, angle E, then angle E and angle H have to be congruent because they're both 64. Okay, so I've now just shown here that angle E and angle H are congruent. So I had my first angle from the right angles. I have a couple 64-degree angles. So since I have this pair of angles, this pair of angles congruent, now I can conclude that triangle CDE is similar to triangle KGH by angle-angle. Now, order matters here. Notice that in these two triangles, C and K correspond to each other. Those are both the 26-degree angles. D and G are both the 90s, and E and H are both the 64-degree angles. So you have to write them in that specific order, okay, or a corresponding order. Okay? So if you write C, D, E, that's fine, but then you have to make sure that your second triangle matches up to what you said there. Okay, let's do a couple more examples here. Now I'm back to writing. Show that the two triangles are similar. Show that triangle ABE is similar to triangle ACD. Well, the only thing that we know right now, just by looking at this, is that angle ABE is congruent to angle ACD. And the reason that you can just say that is because, well, they're both 52 degrees, right? Both 52 degrees. Okay, so since they're both 52 degrees, they're obviously going to be equal to each other. So that's one angle. We just need one more, another pair of angles to be congruent to ultimately show that ABE, this top smaller triangle, is similar to ACD, the biggest triangle. Okay, and now you're like, oh geez, well now what do we do? But if you notice, they actually have this top angle, angle A, in common, right? This angle A right here is in both triangles. It's in that smaller one up top, and it's in the bigger one. So we can say that angle A is congruent to angle A. It equals itself. And there is a property that we talked about first semester when something equals itself. Does anybody remember? Reflexive. You're right. Good job, person in the back. It's reflexive property. So since these are both 52, angle A equals itself by reflexive, now we can conclude that triangle ABE is in fact similar to triangle ACD by angle. So you've shown that you have two pairs of angles congruent. That's why it's helpful to have your theorem table still filled out from first semester, because some of these reasonings we're still going to use. Letter B, triangle SVR, the left one similar to the right one. Okay. These lines right, or these arrows right here show parallel. Okay. So there's a lot of different ways that you can go about doing the steps here. I'm going to first, just as by way of reminder of a theorem, I'm going to say that this one and this one are the same. Why is it that angle SVR has to be congruent to angle TVU? This is by vertical angles. Hopefully you remember that from first semester. So angle SVR has to be congruent to angle TVU because these are vertical angles. The only other thing I know is that I have parallel lines. So once again, you're going to go way back to first semester and you're going to think, what do I know about parallel lines? How can I show angles congruent by parallel lines? Well, if you remember, and hopefully you do, that angle S is going to be congruent to angle U. Because these are parallel, this line SU right here is a transversal, and that transversal is cutting a pair of parallel lines. Okay, so if you remember the rationale here is if parallel, then these are alternate interior angles, and alternate interior angles are going to be congruent. And maybe if you extended these out a little bit, you could see that they're both inside, they're both interior angles inside this parallel, or excuse me, inside, or these. Yeah, inside. I don't know what else I'm trying to say. But hopefully you can see that they are interior versus exterior. They're tucked inside between these parallel lines. So now we've shown, oh, I got a couple angles congruent. Therefore, triangle SVR will be similar to triangle UVT by the only theorem that we have so far to prove triangles similar, and that is angle. So embrace it, because we're going to learn a few more theorems. The only one you have at your disposal right now is angle, angle. So what you should be trying to do is trying to prove two angles congruent. And if you do that, then you've basically finished your proof. Okay. Any questions? No, Mr. Kuiper, you're doing awesome. Great. Okay. Last example, and then we are going to be done. And the person in the back with the annoying voice will be done taking notes. So, a flagpole casts a shadow. I love this question, by the way. A flagpole casts a shadow that is 50 feet long. So here's a flagpole. It's casting a shadow that's 50 feet long. At the same time, a woman is standing nearby who is 5 feet 4 inches tall, and she casts a shadow that's 40 inches long. How tall is the flagpole to the nearest foot? So what I'm going to do is I'm actually going to recreate this with triangles. And this is actually a really cool way, and if it was not the polar vortex still, I would love to be able to go outside and find measures of very tall objects. And the way that you can do that is by this right here. Okay, so here's the woman, here's her shadow, here's going to be the flagpole, here's its shadow. I don't know the height of the flagpole, so that's going to, let me scoot it over. Sorry, this is the woman, shadow, flagpole, shadow. Don't know the height of the flagpole. What do I know? I do know that the flagpole, its shadow is 50 feet. Great. I know the height of the woman. The woman is 5 feet 4 inches tall. Okay, so 5 feet 4 inches tall. And then her shadow is 40 inches long. So we're going to set up a proportion. And the reason that these triangles are going to be similar is because ultimately angle, angle. These are going to both be right angles, and the rays of the sun come in parallel, so then this angle and this angle would have to be the same, so therefore they're all the same. So they are going to be similar triangles. So since they're similar triangles, side lengths are proportional, except we have to be very careful before we start. This is in feet, this is in inches, and this is in both. So we need to just convert this to all to feet or all to inches. And it doesn't matter which one you choose, but just make sure that you are choosing one that is consistent for everything. Okay. And so what I'm going to do here is I'm going to say, okay, if I do height over shadow, this would be x over 50. Then over here, I want this to be height over shadow as well. Okay, so first off, if I put height over shadow, that's fine, but I do want to make sure that I have this in feet, just for consistency. Okay, so the height is 5 feet 4 inches. Well, 5 feet 4 inches, okay, so that's 5 feet, but then 4 inches, okay, since there's 12 inches in a foot, 4/12 is 1/3. So this would actually be like 5.3 repeating, or 5 1/3. Okay. 40 inches. I want to figure out how many feet are 40 inches. Well, once again, there's 12 inches in a foot. So you got 12, 24, 36 would be 3 feet. And you still have 4 inches left over. So this would be 3.3 repeating. And now these are both in feet. Okay. You could have maybe gone inches. Maybe as I think about this, inches would have been a little bit easier. You could have avoided decimals, but hopefully you get the idea that you need to make sure that since the question wants it in the nearest foot, I'm going to give it, just put everything in terms of feet so then you don't have to convert at the end. I converted now. You could have converted at the end. So now when you cross multiply, okay, remember cross multiply this times this equal this times this. So what you'll end up doing is 50 times 5.3 repeating, divide it by 3.3 repeating, and you should ultimately get that the flagpole is 80 feet. Okay. So just a reminder about proportions and a good application of how to do that. 50 times 5.3 repeating divided by 3.3 repeating gets you 80 feet. So the flagpole is 80 feet tall. Very good. Homework is here, and we'll work on that in class.